So here's a quick recap of how log linear models were applied to the tagging problem. So remember we used this notation W1 colon n to refer to an input sentence, W1 through Wn. And similarly, T1 colon n is a tag sequence. The first critical idea was to define the conditional probability of any tag sequence T1 to n conditioned on a word sequence W1 through Wn by first using the chain rule and secondly using independence assumptions. And as a result, we end up as this conditional probability having a product of terms. We have product here from j equals 1 to n. At each point we have the jth tag in the sequence T sub j, and that's conditioned on the entire input sentence and the previous two tags in the sequence. So again, we have a Markov style assumption where the jth tag depends just on the previous two tags, but in addition we condition on the entire sentence at every point. We're left with the problem of estimating these p terms, and that's a complex problem because we're conditioning on a large amount of information. There are a large number of possible features you might want to incorporate in a model which predicts this conditional distribution. So we use log linear models for this task, which, as we argued, are quite flexible in terms of the types of features that can be included. Finally, we used the Viterbi algorithm, once again, to compute the highest probability tag sequence for any input sentence. So given a test sentence, an input sentence, W1 through Wn, we can search for the tag sequence that has the highest value for this conditional probability. And that can be achieved using the Viterbi algorithm. So now we're going to consider how to generalize this approach to a much wider class of problems. We'll focus on the parsing problem, but as you'll see, we'll see some general principles emerge in how we can apply log linear models to more complex problems. And the class of models we'll describe are often called history-based models. They're actually conditional history-based models because we'll be modeling conditional distributions such as P of t given W. So the critical question is the following. Here I'm using the notation capital S equal to the input sentence. I'll use this throughout these slides. How do we define the conditional probability of big T given big S if T is not a tag sequence but rather it's some other structure, for example a parse structure? So how can we generalize the ideas that I showed you for log linear taggers to the case where this structure T might be a parse tree or of some other object, maybe even a translation, for example, of the sentence? So here's a very high-level outline of the approach we'll use, and throughout the rest of this segment of the class we'll instantiate the various choices shown in this outline. So there are essentially three steps, or rather four steps, in these conditional history-based models. The first one is going to be to take our structure, for example a parse tree, and represent it as a sequence of decisions, D1 through Dm. So we'll see very soon that this sequence of decisions basically corresponds to us building the tree in some kind of bottom-up, left-to-right order over the input. Notice that this value m, the number of decisions, is not necessarily the same as the length of the sentence. In the tagging models we saw, the sequence of decisions was essentially the n tagging decisions corresponding to the n words in the sentence. But as we go to more complex structures, we're going to see that the number of decisions can actually be different from the length of the sentence. The second step is to use the chain rule to decompose the probability as follows. So the conditional probability of the tree T given a sentence S is going to be a product of terms where at each point I have the conditional probability of the ith decision in my sequence, and I condition on the I-1 previous decisions, and in addition the sentence, which is input to the model. Now notice here we haven't actually made any Markov assumptions. In the tagging case, we would replace this by di-2 di-1, reflecting the fact that we make a kind of Markov assumption that we just condition on the previous two decisions. In fact, in the history-based parsing models that we see, we're not going to make this assumption. Okay, so we could potentially condition on any information in the context, any information in the sentence being parsed, and any information in the previous sequence of decisions. The third step is going to be to use a log linear model to estimate this conditional probability of the decision given the previous I-1 decisions and the input sentence. And we'll make use of the flexibility of log linear models in terms of the features that they can include. And this will be another setting where we really see the power of log linear models in terms of the representations they can use. The final question is search. So in general, we're going to take some sentence S as input, and we're going to try to find the parse tree T that maximizes this conditional probability T given S, where this of course is defined through this expression here. Now crucially, we're not going to make a Markov assumption in this case, and that means in the general case that dynamic programming algorithms won't be available. We won't be able to make use of the tricks we saw in dynamic programming to give us an exact but efficient algorithm for search in these models. But we'll see that we can use something very similar to the kind of beam search algorithms we saw for phrase-based decoding. We can use a very similar kind of algorithm in this particular context.